In this video, we will see dry run of the code. So now let's do a quick dry run of this code. So here, this is my root node. Okay, so I will denote it with R, and we have P with this one and Q with this one. So, okay, so let's create our LCA function also. So let me create an LCA stack. Okay, and let me quickly take a screenshot so that we quickly erase it. And we will also create a binary tree, right, of LCA. So let's see. So I'm first calling LCA with my root and P and Q. So I am calling LCA. Okay, let me write smaller. So I'm calling LCA with 6 as in root and 3 as in P and Q as in 5. Right. So I will call, let me put L here only because here is not so much space. So L with 6 with 3 and 5. Come here, I will check is my root is equals to null. No, it's not null. Is P dot well, what is P dot well? 3 and is lesser than root dot well. So yes, 3 is lesser than 6 and Q dot well, that is 5. Is it lesser than root dot well? Yes, both are lesser, right? So P dot, this condition is true, right? 3 is lesser than 6 and 5 is lesser than 6, right? So basically I am saying 3, but basically it's 3 dot well, that is 3 only. Q dot well, that is 5. Okay, so both are lesser. So I will return LCA root dot left P and so what is root dot left? So I will call LCA root dot left, that is 2 comma 3 comma 5. So I will call L with 2 comma 3 comma 5. Okay. Once I have called it, again I will check is my root is equals to null? No, it's not. Okay. Is P dot well is lesser? So what is P dot well? That is 3. Is lesser than the root dot well? No, 3 is not lesser than. So I will directly come to here because here end condition is not true. Let's see. 3 is not lesser than 2 and 5 is also not lesser than 2, right? So this condition is not satisfying. P dot well is not lesser than root dot well and Q dot well is also not lesser than root dot well. So I will jump to this condition and I will check is P dot well, that is 3 is greater than root dot well. Yes, 3 is greater than 2 and 5 is also greater than 2. So this condition is satisfying, right? So I will call return LCA root dot right. So I will call LCA with root dot right. What is root dot right? That is 4 and with P and Q. So I will call LCA with 4 P and Q. Now I will again check is my root is equals to null. Again I will check from the here is my root is equals to null. No, root is 4. Is P dot well is lesser than root dot well. So P dot well is lesser. Yes, 3 is lesser than 4 and Q dot well is lesser than root dot well. No, 5 is not lesser. So what I will do, I will come to next condition and I will check is P dot well is greater than root dot well. 3 is not greater than 4 and Q dot well is lesser greater than root dot well. 5 is yes greater than 4. So this condition is not also not satisfying, right? So both the conditions are not satisfied. I will return the node and what was the node? I will return 4. So this here for this function I will return 4, right? Once I have written 4, right, where I will come, right? Which function that called it, right? This function called it, right? So I will return 4 it to it and this will also return. So basically if I am returning LCA 4 comma 3 comma to this function 4, can I say my work of this function is done, right? So I will simply remove from this stack. Now 4 I am getting here. This will return to the function that this called, right? So it will call 2, 3 and comma 5 with a value of 4. So can I say my this function work is also done? Basically it called LCA. LCA got a return value of 4 and now it returned the return value to 235, right? So that function work is also done. So I will remove this from the stack, right? Now who called this LCA235? This called 6345, right? So it will return the value 4 to this function, right? So can I say my work done of this function is also done, right? So yes, I will remove this from the stack. And in the last, what I am getting as a result, I will get answer as a 4 as a root. This is not a value. This is the root node, right? So this is how it will work. Basically, this is a quick dry run of binary search tree. Okay. Now let's talk about the time and space complexity. So see, you are not exploring all the nodes, right? So once you get that both the values are lesser, you will explore this option, right? then you get to know that both the values are greater, you will explore this option, right? So even on the worst case, what you are doing, you are going to the last, right? N minus, I will say, right? If there is a height, if there is a height, you are going till h minus 1, right? Because maybe in the worst case, the last will be the descendant, right? The last will be the ancestor, LCA, right? So you are going in each case, in worst case, right? The height of the binary tree minus 1, right? So the time complexity will be, right, if I'm ignoring the constant, that is only 1, so we can ignore it. So the time complexity again depends on the height of your binary search tree, right? So where h will be the height of the binary search tree. Okay. And what about the space complexity? So space, we are using only recursion space, recursion stack, right? So you can check how many functions are you put it here, 1, 2, and 3. So these functions are also in the height, like basically what are the functions that are coming to the height. So space complexity of the recursion will also depend on the height of the binary search tree. So both are dependent on the height of the binary search tree, and this will be the time and space complexity. Yeah, so that's all for lowest common ancestor of a binary search tree. Again, very good problem in binary search tree. If you want to explore more, try to check out more problems on binary search tree. Okay, so that's all for this video. Okay, I will see you in the next problem with again some binary trees concept.